Okay, let's do the example from section 6.3 where we look at breastfeeding and intelligence here. So in this example, they did a study, this is from 1999, where they looked at children and they wanted to see whether if they were breastfed or bottle fed, whether they could find a difference in intelligence later on. And so early on, they sort of found out whether the children were breastfed or bottle fed. Then 4 years later, they followed up and did the general cognitive index, which is sort of a measure of the child's, intelligence in some sense. And so, you could set up the hypothesis here that the mean on this CGI test for breastfed children minus the mean for bottle-fed children is 0. That would mean that the two populations had the same mean. Or maybe that's not equal to 0. Maybe there's a difference between children who are breastfed and bottle-fed in terms of their intelligence later on. If we look at the data, what we see is there was a large number of people in both samples. There was a difference in the one mean compared to the other one, but when you actually overlay the data, it looks like there's a lot of overlap. So if there is a difference, it appears to be small, and we'll find out whether we can conclude that there is or is not a statistically significant difference. So when you set this up, when you subtract these two numbers, you get 4.4. So that is the difference in the two means. And could you get a difference this big by chance alone, or is the only way to get a difference in means of 4.4 if the two populations were in fact different? And again, this is the question, are the two populations different from each other? Of course, there's going to be a lot of overlap, but are the two populations actually having a difference in means? And can the data actually tell us that that's the case or not? If you're going to do a theory-based test, there are some validity conditions. Number one, you need at least 20 observations in both samples. And because it's quantitative data, we want it to be at least symmetric or not strongly skewed. Let's go back to the data. We can see these the box and whisker plots appear to be fairly symmetric. The dot plots don't really appear to have very much skew here, so I think the theory-based test is valid. And what you're going to do then is you're going to go to the applet, okay? And if you were doing a simulation-based test, you would use the multiple means applet. If you wanted to do a theory-based test, you'd use the theory-based applet. Actually, if we just click through to the multiple means applet, we can, I think the data for this one is this breastfed data here, which I've got here. We can copy it, we can paste it into this thing. It makes the bot, makes kind of a dot plot of the data, does the statistics, which we saw, does the difference of 4.4, and then you could do a simulation to see if, could you get, could the difference in observations be different? And we've done that before in section 2. What we want to do here is go to the theory-based applet. We're switching it to two means. We're going to paste in the data. I believe it is stacked and includes the header. And there we go. We get a histogram of the data here and the data here. It computes the difference in sample means to be 4.4. If we didn't have the data, you could just write in the summary statistics, the sample size, the sample means, and the sample standard deviations and do it that way. Since we had the data, we just pasted it in. And then all you have to do is click this little button that says test of significance. And what it does is it will calculate a p-value for you. So what is the probability of getting a difference at least this big if in fact the two populations were the same? And what you see is that the p-value is quite small. And that's going to tell us that we have a reason to conclude that the two population means are in fact different. How much different? Confidence interval will tell you how much different. Somewhere between 0.86 and 7.93 points on this CGI score. So what we might conclude is that children who are breastfed, I believe it was breastfed, had the higher score, yes. So children who are breastfed we would expect them, or we would be 95% confident that their average CGI score is between 0.87 and 7.93 points higher than the average score among children who were not breastfed, is essentially the conclusion we could make based on this data. And that's how the applet does it for you. If we do go back just for a second to the simulation-based applet, you can click this this show ANOVA table, and it will compute the p-value for you as well. So in a sense, you can do a theory-based test on the simulation applet as well. It just sort of looks a little bit different, but they give you the confidence interval as well. They put a little asterisk there indicating that it doesn't include 0 because we already concluded that 0 wasn't plausible when we rejected 0. All right, let's go back to the slides. So the T statistic is similar to the Z statistic. That's another way of categorizing the strength of evidence. If we look at this, I believe it computed the T statistic for us as 2.46. So remember, that's sort of a measure of how many standard deviations this sample the difference in the sample means is from 0 in the null distribution. That's bigger than 2. That's why we're getting strong evidence here. The computer's going to do that for us. There is a way to calculate it by hand, but we're not going to worry about that. All right, we got the p-value. So we made that conclusion that if breastfeeding were not associated with GCI score at age 4, the probability of observing a difference at least as extreme as 4.4 by random chance would be only 0.015, which is why we rejected the null hypothesis in favor of the alternative. So what do you conclude? Yeah, breastfed babies appear to have a higher average GCI score at age 5 or at age 4. The confidence interval predicts that the average GCI score for breastfed babies is somewhere between 0.87 to 7.93 points higher. 0 is not in the interval. We already concluded it was statistically significant. And then let me just finish with one comment. This was an observational study. They did not flip a coin and determine whether the babies were breastfed or bottle fed, which means we shouldn't be concluding cause and effect here. And there's any number of confounding variables that could be connecting whether the babies are breastfed or bottle fed and their intelligence. I mean, it could be socioeconomic status or education of the parents. There's so many different things going on here. So a lot of people might say, oh, if you breastfeed, then boom, you increase your kid's intelligence. Well, that's not a valid conclusion from this study. We've just shown that there's an association between breastfed, bottle fed, and GCI score, at least at age 4. And the other thing you want to know is this difference in score is very small, right? There's a huge amount of variation in this. And so the fact that it's significant doesn't mean that it's practically significant. It is statistically significant, but not necessarily practically significant. This confidence interval shows, where'd the confidence interval? Shows that even if, and we did not conclude this, but even if breastfeeding, say, caused your GCI score to be higher, it doesn't even have that much of an effect. All right, so that's how you do this. Just another look at the test here. Paste the data in, hit the use data button, you get the thing. It subtracts to see the difference. And then when you click here, test of significance and confidence interval, it shows you the standardized statistic, the p-value, and the confidence interval. And that's how you do a theory-based test. And you can tell from the data that it's pretty symmetric, not very skewed, so there's no danger. And there's at least 20, right? The sample size was big here, so there was plenty of data for us to do a theory-based test. All right. So that's section 6.3, comparing two means using a theory-based approach.